Uh, Good morning, dear students. Today we want to study about the standard enthalpy of formation. So let us study about the standard enthalpy of formation. Now here the new word is being introduced which is known as the standard. So let us understand what is the meaning of the word standard here. Let us study about the standard enthalpy of formation. A standard enthalpy change for the formation of one mole of a compound from its element in their most stable state of aggregation, also known as the reference state, is called the standard molar enthalpy of formation. See, most stable state is the stable state which is present at a room temperature. For example, iron. So the solid state of iron is the most stable state. Water liquid state is the most stable state. So this is how, my dear students, when it comes to the most stable state, the standard enthalpy change for the formation of one mole of compound from its element in their most stable state of aggregation, also known as the reference state, is called the standard molar enthalpy of formation. The symbol is delta FH bar, that is standard, where the subscript F indicates the 1 mole of compound has been formed in the standard state of element in their most stable state of aggregation. So, my dear students, when some compound is formed from its most stable state, this stable state is also known as the reference state. So, the reference state of an element is its most stable state of aggregation at 25 degrees centigrade and 1 bar pressure. The most stable state or the reference state of an element is the most stable state of aggregation at 25 degrees centigrade and 1 bar pressure. That is what it is, the state when we generally consider it as a room temperature and pressure or laboratory conditions. The reference state of an element is the most stable state of aggregation at 25 degrees centigrade and 1 bar pressure. For example, the reference state of dihydrogen is H2 gas. For oxygen, it is O2 gas. For carbon, the reference state is graphite. Please understand that for carbon, the reference state is graphite. For sulfur, the rhombic sulfur, the rhombic sulfur is the most stable state or reference state of sulfur. So this is how, my dear students, these are the examples of their reference states or most stable states. Some reaction with the standard molar enthalpy of formation are given below. See, you can see here that in this particular reaction, water is made from hydrogen gas and oxygen gas. So when water, which is in the liquid state, is made from the hydrogen in the gaseous state and oxygen in the gaseous state, during this change, this is the thermodynamic change. During this change, the change in enthalpy, because this reaction takes place at constant pressure, so during this change, the change in enthalpy is minus 285.8 kilojoule per mole. It means that the energy is produced during this reaction, and this is what it is known as the standard or molar enthalpy of formation of water. Please remember that the reactants and products must be in their stable state. Same way, when we want to prepare methane, we take carbon which is in the graphite form and it is in the solid form. Same way, my dear students, we study about the hydrogen gas and we take hydrogen as a gas and we take methane as a gas. So from carbon and hydrogen, methane gas is produced, and this is how, my dear students, the change in the enthalpy is minus 74.81 kilojoule per mole. It means the energy is produced during this reaction when methane is formed, and this is what it is known as the standard molar enthalpy of formation of methane. So this is the energy it is produced when 1 mole of methane is produced from its standard state of graphite carbon and the hydrogen gas. Same way, my dear students, if you want to prepare ethanol, then we can prepare ethanol from the carbon, that is graphite, in solid state, hydrogen which is in the gaseous state, and oxygen in the gaseous state. And the ethanol that we should get should be in the liquid state. And during this change, the enthalpy change is 277 plus 7 kilojoule per mole. That means the energy is required to prepare ethanol. And this is how, my dear students, we understand this change. So this is what it is known as the standard molar enthalpy of formation of ethanol, or this is the energy change that takes place when 1 mole of ethanol is being produced. So it is important, my dear students, here to understand that the standard molar enthalpy of formation is just a special case of standard enthalpy of reaction. What is special? That during the reactions, the reactants and products must be in their standard states. So during the reaction, if the reactants and products are in the standard state, then the enthalpy of reaction can be considered as the enthalpy of formation. Remember that the temperature should be 25 degrees centigrade and the pressure should be 1 bar. Where 1 mole of a compound is formed from its constituent elements, as in the above three equation, we have seen that 1 mole of each, we have seen that 1 mole of each is 1 mole of water, 1 mole of methane, and 1 mole of ethanol is formed. Please remember, my dear students, that the substances should be produced from their element directly. So this is how it is very necessary that during the formation the substance should be produced from their element. In the contrast, exactly opposite to it, the enthalpy change for the exothermic reaction, you can see here, we have calcium oxide. Calcium oxide reacts with carbon dioxide and we get calcium carbonate. During this reaction, calcium carbonate is produced. But calcium carbonate is not produced from the element calcium, carbon and oxygen. But it is produced from the other compound, which are calcium oxide and carbon dioxide. And that is why we cannot consider this energy is not the enthalpy of formation of the calcium carbonate. So this is not the energy of the formation of the calcium carbonate, or during this reaction, whatever the enthalpy change takes place is not the enthalpy of formation of calcium carbonate. Please understand this, that this is not the energy of formation of the calcium carbonate. It is written here, it is not an enthalpy of formation of calcium carbonate. Since the calcium carbonate has been formed from the other compounds and not from its constituent elements. Same way, my dear students, also from the reaction given below, enthalpy change is not standard enthalpy of formation. You can see that here we have got the hydrogen gas and bromine gas is produced and HBr is produced in the gaseous state. Here the enthalpy change of the reaction is minus 72.8 kilojoule per mole. Here 2 moles instead of 1 mole of HBr is produced. You can see here that instead of 1 mole, here 2 moles are produced. So this is even not the enthalpy of formation of HBr. Though HBr is produced from the element hydrogen in its standard state, bromine in its standard state, HBr is also in its standard state. But still, the enthalpy reaction is not actually the enthalpy of formation of HBr, because HBr is produced 2 mole. Instead of 2 mole, we should have only 1 mole produced. So the reaction what we have seen or we have been watching is it should be actually 1 by 2 H2 gas plus 1 by 2 Br2 gas, that gives HBr gas. This is how it should go on. So my dear students, what I simply mean to say is that this energy, whatever it has been produced, has to be divided with 1 by 2. Because this is the energy that is not kilojoule per mole. Here we cannot write it is kilojoule per mole because it is kilojoule per 2 mole. So we need to divide this energy. Here 2 moles instead of 1 mole of product is formed from the element, and that is why the delta reaction enthalpy is 2 times the enthalpy of formation of HBr, and that is why we need to divide this enthalpy of formation of HBr with 2, and that is how the enthalpy of formation of HBr can be calculated. Therefore, by dividing all the coefficients in the balanced equation by 2, expression for the enthalpy of formation of HBr gas is written. So we will write it in this form, and this is how we will get the enthalpy of formation of HBr is minus 36.4 kilojoule per mole. Standard enthalpies of formation of some compounds can be calculated carefully this way. So this is how, my dear students, by producing any compound from its elemental form, we can carefully calculate the standard enthalpy of formation. By convention, standard enthalpy for formation, that is delta F H bar of an element is reference state, that is its most stable state of aggregation, is taken as 0. Now, my dear students, here it is trying to tell that if you want to prepare carbon in the solid form, that is the graphite. So this is what it is, the reference state, or it is the most stable state for carbon, and that is why the enthalpy for formation of carbon in solid state is taken as 0. So during the calculation, if you are given the carbon solid graphite and if you want to put its enthalpy of formation, then you will put 0 answer for this. So when we will calculate, we will understand these things better. I have taken example to make you understand this. Suppose you are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime and carbon dioxide with all the standards in their standard state. So my dear students, if you are an engineer and you want to know how much heat is required to decompose calcium carbonate, here you provide heat and you decompose this. So what you need to know this answer, that what is the enthalpy of reaction for 1 mole of calcium carbonate. And by knowing this, you can easily understand that how much energy is needed to break the calcium carbonates into the calcium oxide and calcium carbon dioxide. So here we can use or can make use of the standard enthalpy of formation, and we can calculate the enthalpy change for the reaction. So if we calculate the enthalpy change for the reaction of the decomposition of calcium carbonate, we should actually get the information about the enthalpy of formation of calcium carbonate. The following general equation can be used for the enthalpy change. So my dear students, we are all aware that enthalpy of reaction is the summation of enthalpy of products minus summation of enthalpy of reactants, where A and B are the coefficient of the products and reactants in the balanced chemical equation. So here in this case, my dear students, the decomposition of calcium carbonate, we have A is equal to 1 and we have B is equal to 1 for, and therefore delta R is equal to delta formation of calcium oxide solid, delta formation of carbon dioxide gas, and delta formation of H bar calcium carbonate. Let us put the value here, that formation of calcium oxide is minus 635.1 kilojoule per mole. This formation of carbon dioxide is minus 393.5 kilojoule per mole, and formation of calcium carbonate is minus 1206.9 kilojoule per mole. And by doing all this calculation, we can see that 178.3 kilojoule per mole of energy is required to decompose 1 mole of calcium carbonate. So this much of energy should be provided to the calcium carbonate so that 1 mole of calcium carbonate can be decomposed. So depending upon the mass of the calcium carbonate that I take, I can determine what amount of energy I need to provide so that I can decompose all the calcium carbonate that I have. Thus, decomposition of calcium carbonate solid is an endothermic reaction because it requires energy, and we need to heat calcium carbonate for getting the desired products. This is how, my dear students, with the help of the calculation, we understand and we can use the enthalpy of formation. Now, my dear students, we want to understand about the equation. Till now, we have used the balanced chemical equation, but now we are going to use the new kind of equation, which is known as the thermochemical equation. So let us define what is thermochemical equation. A balanced chemical equation together with the value of its delta RH, that is the delta, that is the enthalpy of reaction, is called the thermochemical equation. So a balanced chemical equation which is represented with the enthalpy of reaction is known as the thermochemical equation. Here we specify the physical state along with the allotropic state. Please remember, my dear students, that here we specify not only the physical state, but we also specify the allotropic state of the substance in the equation. You can see here that I have written carbon. With carbon, I have written solid. So it is in the solid form, as well as we have written that it is in the graphite form. Because carbon can be in the diamond form, carbon can be in the full ring form. But when carbon is in the graphite form, it is its reference state and it is its standard state. So this is how in the thermochemical equation, we not only represent the physical state, but if the element is having allotropic forms, we also represent it in the form of its allotropic forms also. So here, my dear students, these two carbon reacts with the hydrogen and oxygen to produce ethanol. Here the enthalpy of reaction is minus 277.7 kilojoule per mole. Same way, my dear students, when we write the ethanol, which is liquid, that reacts with the oxygen gas, we get 2 mole of carbon dioxide and 3 mole of liquid. You can see here that with the balanced chemical equation, we have represent the enthalpy change, and this is how we understand the thermochemical reaction, my dear students. Now, my dear students, let us understand the conventions. Conventions are the ideas or thoughts which are given by the organization that makes us understand the various rules to understand the various terms or how to represent them mathematically. The stoichiometric coefficient in a balanced chemical equation refers to the number of moles and not the number of molecules. Please remember. So whenever we write a thermochemical equation and when we write the stoichiometric coefficient, it always represents the number of moles and never represents the number of molecules, because the enthalpy change we write it as a kilojoule per mole in that unit. So in thermochemical equation, all the stoichiometric units or all the stoichiometric coefficients represents only the number of moles. The numerical value delta RH refers to the number of moles of substance specified by an equation. So these numerical values of this delta reaction enthalpy refers to the number of moles of substance specified in the equation. A standard enthalpy change, that is the formation of enthalpy, will have units like kilojoule per mole. So when we write a thermochemical equation, we write the enthalpy change into the unit like kilojoule per mole. Let us understand one example. Calculate the enthalpy of reaction for Fe2O3 plus 3H2, that gives 2Fe plus 3H2O. Here what information we are given, that enthalpy of formation of water in liquid state is 285.83 kilojoule per mole. Enthalpy of formation of Fe2O3 in the solid state is minus 824.2 kilojoule per mole. Enthalpy of formation of iron solid is equal to 0. See, here you can easily understand that formation of iron in its standard state, that is the solid state, is equal to 0, and enthalpy of formation of hydrogen in its gaseous state is also equal to 0 as per convention. So when we take the elements into their elemental form and when we study them, we realize that their enthalpy of formation are taken as a 0. So my dear students, it's quite simple to understand that we will write that enthalpy of reaction is equal to sigma I H products minus sigma Bi H reactants. So it is 3 times the enthalpy of formation of water plus 2 times the enthalpy of formation of iron minus enthalpy of formation of Fe2O3 multiplied by 3 times the enthalpy of formation of hydrogen. Why do we put this? Because we already have the stoichiometric coefficients present into the balanced chemical equation. So their enthalpy of formation per mole has to be multiplied within their number of moles. Here we put the value for these elemental substances. The enthalpy is kept as 0. You can see here in case of iron and in case of oxygen, we have put the value 0. And by this calculation, we find out that the change is minus 33.3 kilojoule per mole. So my dear students, if we want to prepare the iron in solid form, we'll have to divide this equation with 1 by 2 because we get 2 moles of Fe. So for the production of Fe, we can here simply divide the equation with 1 by 2, and that is why the formation of enthalpy of formation should also be divided with 2. And finally we get the answer. Enthalpy of reaction is minus 16.6 kilojoule per mole. So same way my dear students, we can even understand or we can write the thermochemical equation as 2Fe plus 3H2O liquid, Fe2O3 solid plus 3H2O. Actually delta H is plus here. So we have just reversed the equation and then we have put the value plus. So whenever a chemical equation is reversed, the value of the reaction enthalpy is reversed in its sign. So these were the very important